Hello, my name is Andrew Guger, and I was assigned to explain the merge sort algorithm. So what is merge sort? So merge sort is a divide and conquer sorting algorithm that makes use of recursion. Divide and conquer, as you'll see later in the example, kind of means to take the unsorted array or data and break it down into smaller pieces, and then sort it as you kind of build it back up. And the algorithm does make use of recursion. So let's break it down first. Say you're given an array of 5, 13, 263, 1, 22, and 18. So the first step is to divide the array down into individual pieces, right? So we take this array and then we split it in half. So then we have two arrays of 5, 13, 263, and then the other one is 1, 22, and 18. And then we further break this down into three different arrays of 2, and then eventually each and every single data piece will exist in its own array. Think of it that way. So once we have it all broken down, then we're ready to sort. So we're going to take each individual data piece and then merge them with its neighbor. And we're going to make a few small arrays. And then while we're doing that, we're placing them in the correct order, right? So here we have them all separated. So 5 and 13 are going to be placed together into one array, right? So this is the output here. Those didn't have to be swapped. Then 263 and 1, these have to be swapped. So it's going to be 1 and 263. Then 22 and 18 and 22 are going to be swapped to be put in order. So now we are rebuilding. We will repeat step 2 until the array is fully sorted and it's completely merged as well. So as you can see here, we have the three sets of 2, right? Array of length 2, and then we combine it to have two arrays of 3 data pieces inside, and it is all getting merged as we combine it, right? So this 5, 13, and 1 becomes 1, 5, and 13 in one array, and then 263, 18, and 22 becomes 18, 22, and 263. And then eventually you do combine them all into one data set. And coincidentally, this one going from this piece right here to this final sorted array, it didn't need any sorting, but sometimes you still need to sort for that last step. So now our array is merged. So in terms of runtime and space complexity, for the worst best in an average case, it's all O n times log of n. That's because no matter what, you're always going to be breaking it down and going through and merging and then like building it back up. So this is a really effective sorting algorithm. I think it's much more effective with larger data sets. I think in terms of smaller data sets, there are other algorithms that might be a little bit more effective. And then in terms of space complexity, and that's the amount of memory that an algorithm takes up in order to run. So merge sort is O of n for space complexity, which I mean believes that it's linear as the amount of data increases, so does the amount of memory needed to run the algorithm. So what about stable and in place? So stability is preserving the order in which the same piece of data appears in the data set. And I have an example of this later. So if you have a whole bunch of numbers and you have a 6 appear somewhere, and then you have another 6 appear a little bit later on. So when we end up sorting the algorithm, or sorting the data set, that first 6 that was given to us gets put first, and then that second 6 gets put. Not, the second 6 doesn't go before the first one. So just by the fundamental method of how merge sort works, that's always going to preserve stability, just because you break it down into individual pieces and then you plug it back in and build it up together. And then in place. So that just means sorting the data as given to you without making a copy. And not just copying one individual piece to check it against other pieces within the data set. So merge sort is not in place, since you must create multiple arrays, copies of the array as you go, and different versions. So here's another step-by-step walkthrough. Right, so we're given this array of 6, 132, 33, 6, 59, 60, 89, and 7. So the first step is we're going to break it down in half, right? So now we have 2 arrays, 6, 132, 33, and 6, right? And then 59, 60, 89, and 7. And then we continue doing this, right? So now we have 4 arrays of 2, numbers in each. And we keep doing this until each and every data piece gets put in its own array, right? So once we have that, then we continue on. Now we want to rebuild it up, right? So we're rebuilding it and merging it. We're actually merging it together. And so we're going to merge it with its neighbor, and that's when the sorting comes in, right? So 6 and 132, that gets put together. 33 and 6, that gets put as 6 and 33, right? Because now we're actually starting to sort it as we combine it, as we merge it, right? And then 59 and 60, then 7 and 89. And then we continue this, right? So now we can combine these two arrays, 6, 132, 6, and 33. So that becomes 6, 6, 33, and 132, until you get your final sorted array, 6, 6, 7, 33, 59, 60, 89, and 132. And did you catch my example of stability? Right there, see? So we got our first 6 that was here, and then our second 6, and these are, it's preserved stability because it came in this order, right? This 6, so this 6 will have to be second, and this 6 has to be first. So in terms of the applications of merge sort, sorting data sets. So this works with external sorting, which is a class of sorting algorithms that can handle massive amounts of data. I spoke a little bit about that earlier. And then merge sort is better to be implemented using arrays as opposed to linked lists. Thank you. I hope you learned a little bit more about merge sort.